coefficient of kinetic friction. Coefficient of kinetic friction. Now, what that enables us to do is to calculate the amount of friction between any two surfaces. Right? We kind of looked at a little makeshift experiment yesterday where I was pooling a box, and we found that the ratio of kinetic friction force to the normal force for the box that we were working with on the desk was always a certain number. And then we were able to use that number to calculate how much friction there would be between the box and the surface. So if you turn in your book, please, to page 129, and just take a look at the top. There's a table there. The title of the table is Typical Coefficients of Friction. And then column 1 describes different surfaces. So you have rubber on dry concrete, rubber on wet concrete, wood on wood, steel on steel when it's dry, and steel on steel when there's oil. And in the second column you have mu sub s. That's going to be your coefficient of static friction. We're going to talk about that today. And then the third column is the coefficient of kinetic friction. And so you see those numbers vary. And you look at the one rubber on dry concrete, the number is higher than the one for rubber on wet concrete, right? And so what that's telling us is that on wet concrete, so between a rubber tire, for instance, and wet concrete, there's less friction. So let's say that you were driving along the road in your car, which has rubber tires, and you have a dog runs out in the middle of the road. You don't want to hit it, hopefully, so you slam on the brakes, right? You want a dry surface, right? You want as much friction as possible so that it stops before it hits the dog. If it's a wet surface, your coefficient is going to be reduced according to that table, and then you're going to slide. You're more likely to slide because you're to have less friction. And then if it's ice, it's even less friction, right? So it's even a greater chance of not stopping in time. So let's say that your car was 1,000 newtons, right? This equation lets us calculate the friction. So when the road is dry between rubber and concrete, your friction force would be the coefficient of kinetic friction, which in that table is 0.65 times the car is 1,000 newtons. Fg down is 1,000. That means your normal force is 1,000. So this is times your normal force. So let's say you would have 650 newtons of friction. Versus if the road was wet, you would have 0.40 is what it tells you the coefficient is times 1,000. So you'd only have 400 newtons of friction. And then if it's ice, it's going to be even a lower number, so you're going to have even less friction. Okay, so that number is going to be able to help us find out how much friction we can have. You have a small child dragging a heavy rubber-soled shoe by its laces across a concrete sidewalk at constant speed of 0.35 meters per second. If the shoe's mass is 1.56 kilograms, what is the component of force exerted by the child? So how much force does he need applied to the boot to make it move at a constant speed? And the coefficient of kinetic friction is for rubber on concrete, 0.65. All right, so we got a concrete surface, and then we have a rubber-soled boot. So this is going to be a boot.
It's a boot?
It's going to be. Best boot all day. I'm trying.
Can you give it a steel toe?
Steel toe? Well, what does that look like? Just kind of like
Yeah, like that. Just make it a little darker.
a little darker.
There you go.
It's a boot. Let's round it off there. Okay. And it's got these laces, and the child is pulling on them. So he's pulling with a force this way. Huh?
Got a lot of laces.
They're frayed, yeah.
Afraid.
So he's pulling this way. The velocity is this way, and the acceleration is 0. How do we know the acceleration is 0? Constant, right? The number doesn't matter. 0.35 doesn't matter. You don't need that data, but you need to know it's constant. Now, if I draw the free body diagram for the boot, we have Fg down, which is always equal to mg. So that's 1.56 times 9.80, which comes to 15.3 newtons. So that is the weight of the boot. It's on the ground, so there's the normal force, 15.3 newtons. And now the child's pulling on it. So there's going to be a force this way from the child. So we're going to put an FC there for the force from the child. It would really be the tension in the laces, but that's fine. We put force of child. And since it's moving at a constant velocity, we know that the friction force, the kinetic friction force, has to equal the force that way, right? Because all the forces are balanced. And what we want to find is FC, how much force is the child applying? Well, the other piece of information we know is that between rubber and concrete, that the coefficient of kinetic friction is 0.65, because that information is given. So knowing that and knowing our normal force, we are now able to find out what is the friction force. So the force of kinetic friction is found by mu k Fn, and mu k is 0.65, it's given. We found our normal force is 15.3, so that means the kinetic friction is going to be 9.9 newtons. So if the kinetic friction is 9.9, and we already said that we have balanced forces, then that means the force from the child is 9.9. So that's our answer, 9.9 newtons. So from 0 to 6, we're working with what kind of friction?
Static.
Static, right? That word static means stationary, so we're dealing with static friction. So the value of static friction in this case was actually able to go from 0, which is what it is right now because there's no force applied, and it was able to go up to 6. So that means the maximum amount of static friction between this particular box and this surface, giving that amount of weight, is 6 newtons. So what we could say is that the actual friction force, static friction force, varies. It can be less than or equal to 6 in that case. Now if we look at our equation for coefficient of kinetic friction, it takes this form. So it's the coefficient of kinetic times the normal force. Same thing is going to apply for static friction. This is kinetic here. The static friction force will be less than or equal to, however, the coefficient of static friction times the normal force. Less than or equal to because it could be 0, and it can go all the way up to a maximum value, which will equal the static coefficient times the normal force. You need to move a 105 kilogram sofa to a different location in the room. It takes a force of 102 newtons to start it moving. What is the coefficient of static friction between the sofa and the floor? So let's look at the free body diagram for this couch. We have Fg down. It's equal to mg. So that's 102 or 105 times 9.8. So we got 1,029 newtons. Means our normal force is the same. Now what the problem tells us is that we need to push with the force of 102 newtons. So I start pushing, the couch doesn't move. So I keep pushing harder and harder, and I reach up to 102 newtons of force. And once I hit that amount, the couch starts to slide. So that means this maximum static friction, the maximum in this case, was 102 newtons. So knowing that, and knowing now we have this equation to find it, we are interested in getting to the maximum amount. That's going to be the coefficient times the normal. So we can change that to an equality now because we're interested in when it's the maximum. And so mu s is going to be force of static friction over the normal force equals 102 newtons over 1,029 newtons. You see your newtons cancels because it's just a ratio here, and we get 0.099 to be your coefficient of static friction.